Hey everyone, and welcome. Today, we're going to talk about something that's literally everywhere. Something so basic we barely even notice it. We're talking about matter. You know, the stuff that makes up, well, everything. You, me, this planet, the entire universe. So let's get into it. All right, so let me start by asking you a question. Just think about it for a second. What could the air you're breathing right now, the fiery stars light years away, and a single drop of water possibly have in common? They seem like they're from different worlds, right? But they all share a fundamental secret. And there it is. The answer is matter. They are all made of matter. The basic idea is this. If something has mass, if you can weigh it, and it takes up space, then it's matter. It is the universal building block for everything. But what is matter, really? I mean, what's it made of? To get that answer, we have to zoom in. No, I mean way, way in. We're about to leave the world we can see behind and enter a totally invisible world, a world made of tiny, tiny particles. Now, you might think, okay, of course, it's made of particles, but for ages, scientists were really stumped by this. They'd look at a block of wood, and it feels completely solid, right? So they had this huge debate. Is the wood one continuous solid thing, or is it more like a sandy beach made up of trillions of tiny individual bits? So how'd they finally figure it out? Well, with super simple experiments, just like this one. You can do this at home. You mark the water level, stir in a spoonful of salt, and watch it vanish. But here's the crazy part. The water level doesn't go up. So where did the salt go? It didn't just disappear. The tiny salt particles actually slipped into the empty spaces between the water particles. This was proof. Matter isn't solid all the way through. It's made of bits with gaps in between. And when we say these particles are small, we are talking unbelievably tiny. There's this experiment where you take just a couple of little purple crystals of potassium permanganate and drop them in water. They can color a huge amount of water. And then you can take a drop of that water and color another huge container. You can do this over and over. That just goes to show there must be millions and millions of particles in just one tiny crystal. They're literally small beyond our imagination. Okay, so everything is made of these ridiculously small particles. Got it. But what are they doing all the time? Well, it turns out they follow three, let's call them the golden rules, that pretty much explain everything about the physical world. All right, here's the rundown. Rule 1. As we saw with the salt and water, particles have empty space between them. Rule 2. They are never, ever still. They're constantly jiggling and moving around. And Rule 3. They're always kind of pulling on each other. There's a force of attraction. So let's dig into each one. This constant movement, it's called kinetic energy. And here's the really important part. Heat is the key. The hotter particles get, the more kinetic energy they have, and the faster and crazier they move. You know that feeling when someone's cooking something amazing and you can smell it from another room? That's kinetic energy in action. Those little aroma particles are supercharged with heat, letting them zip through the air all the way to your nose, way faster than if the food were cold. And this whole process, this natural tendency for particles to spread out and mix together all on their own, it's got a name. Diffusion. It's happening everywhere, all the time. It's why that food smell fills the whole kitchen. The particles are just doing their thing, constantly moving and spreading out. And finally, rule number 3, attraction. Particles are always pulling on each other. It's kind of like these Edu Mishmi dancers you see here, locking their arms to stay together as a single cohesive group. The particles of matter do the same thing. And the strength of that pull is what really determines, well, just about everything. And this is where it all comes together. This is the big aha moment. You take those 3 rules, the spaces, the constant motion, and the attraction, and when you put them together, boom, you get the 3 states of matter that we see every single day: solids, liquids, and gases. Okay, so this table breaks it all down perfectly. In a solid, those attraction forces are super strong and the particles are packed in tight. They're jiggling, but they can't go anywhere. That's why a rock has a definite shape. In a liquid, the particles have a bit more energy. They can break free and slide past each other, which is why water flows and takes the shape of its glass. And in a gas, the particles have so much energy, they've basically escaped each other's grip completely. They're just bouncing around like crazy, filling whatever space you give them. And this picture, it says it all, doesn't it? Just look at the solid. It's this neat, orderly, tightly packed structure. Then you have the liquid, where things are a little more chaotic, but still pretty close. And then the gas. It's just pure chaos. Particles flying all over the place, super far apart. It's all just a battle between the energy pushing them apart and the attraction pulling them together. So, if the state of matter is all about how much energy its particles have, that must mean we can change it, right? Absolutely. By pumping in energy or taking it away, we can actually force matter to go from one state to another. And the secret ingredient for all of this? It's super simple. It's just energy. Usually, we're talking about heat. You add heat, you can turn a solid into a liquid and a liquid into a gas. You take heat away, you can go right back down the ladder.
But hang on, here's a weird little quirk. Have you ever noticed that when ice is melting, the temperature of the water stays at a perfect 0 degrees Celsius until every last bit of ice is gone? You're adding all this heat, but the temperature isn't changing. So where is the energy going? It's doing a secret job. We call it latent heat or hidden heat. All that energy is being used to break the bonds holding the ice particles together. It's not raising the temperature, it's changing the state.
And this diagram? This is the whole story in one picture. You can see how adding heat leads to melting and boiling, and how removing heat causes condensation and freezing. Energy is the engine that drives every single one of these changes. And then you get the really cool party tricks. Some stuff, like dry ice, which is just solid carbon dioxide, can go straight from a solid to a gas. Poof! It just skips the whole liquid phase entirely. This awesome process is called sublimation. It's what happens when particles get so much energy so fast, they just break free from their solid structure all at once. All right, that's a whole lot of science. But you might be wondering, okay, that's neat, but why does this actually matter to me? Well, let's bring it right back to something we all deal with, trying to stay cool on a blistering hot day. Well, when you sweat, your body is basically being a brilliant physicist. For your sweat, which is a liquid, to turn into a gas and evaporate, it needs energy. And guess where it gets that energy? It steals it, right from your skin. That's the latent heat of vaporization we just talked about. Those little sweat particles are literally pulling heat from your body to power their great escape into the air, which leaves you feeling cooler. And that is exactly why we all reach for cotton t-shirts when it gets hot. See, cotton is fantastic at absorbing your sweat, but more importantly, it spreads that moisture out over a huge surface area. This exposes more of the sweat to the air, which makes it evaporate way faster. And as we just learned, faster evaporation means more heat is being pulled away from your body more quickly. It's like having your own personal high-efficiency cooling system. So when you boil it all down, everything around us is just a collection of tiny particles. And whether they're a solid, liquid, or gas is just a battle between their energy and their attraction to each other. But that leaves us with one last huge question. If these three states are what we get here on Earth under normal conditions, what happens at the absolute extremes of the universe? What kind of matter exists inside our sun, or at temperatures colder than anything we can imagine? That's where you'll find other stranger states, like plasma and Bose-Einstein condensates, which just proves there's always something new and amazing to discover.